Welcome to the AI Paper Podcasts. Today we're diving into a really interesting study from Google DeepMind and J.K. Linz.
That's right. It's called LLMs Are Greedy Agents, Effects of RL Fine-Tuning on Decision-Making Abilities.
And it tackles something pretty fundamental. Why do these incredibly powerful language models sometimes, mess up basic decisions when they're supposed to be acting like agents?
Exactly. They're amazing with language, with common sense, but decision-making in an environment, that seems to be a different challenge.
Right. So for everyone listening, especially you AI researchers and ML engineers, this deep dive is about figuring out why LLMs stumble and how this technique, reinforcement learning fine-tuning, or RLFT, might fix it.
Okay, so here's the quick version for the first minute. LLMs, even advanced ones, often make bad choices. Why? Well, the paper points to three main things. They can be too greedy, sticking with the first good option they find.
Okay.
They also show frequency bias, meaning they just copy common actions from their input. And there's this knowing-doing gap. They might know the right strategy, but don't actually use it.
Got it. So greediness, frequency bias, knowing-doing gap.
Yeah. And the core idea here is that reinforcement learning fine-tuning, specifically using the LLM's own chain of thought reasoning, can really boost their ability to explore options and make better decisions. We see this in tasks like multi-armed bandits and even Tic-Tac-Toe.
And combining RLFT with other exploration tricks helps even more.
Precisely. Guided exploration seems key. So that's the essence we'll unpack.
Perfect. So let's dig into that first failure mode you mentioned, greediness. What does that actually mean here? It's not like the LLM wants more GPUs, right?
No, not quite. Greediness here means the model jumps on the best action it's seen so far, and then just sticks with it. It doesn't explore enough to see if there might be something even better out there.
Okay. Like always going to the same decent coffee shop without checking if a great one opened next door.
Exactly that. It settles too early, potentially missing much better rewards in the long run because it didn't explore widely enough at the start.
And the paper shows this with experiments. I think you mentioned multi-armed bandits.
Yeah, they used AMBs, multi-armed bandits with 10 and 20 arms, kind of like slot machines where you have to figure out which one pays out best by trying them.
Okay.
They tested different sizes of the Gemma II model, 2 billion, 9 billion, 27 billion parameters. And they also looked at whether using chain of thought, getting the model to reason step by step helped.
And did Co-T help? Or were even the big models still greedy?
Well, that's the interesting part. Even the huge 27B model, and even when using Co-T, still showed significant greediness. They found, I think it's in figure 3 in the paper, that after 50 tries, sometimes up to 55% of the possible actions just hadn't been tried at all.
55%. Wow, that's a huge amount of unexplored space.
It really is. And the consequence is what they call suboptimal regret. The LLMs just weren't performing as well as a standard exploration algorithm like UCB upper confidence bound.
Because they got stuck too early.
Yeah, their action coverage, the number of unique arms they pulled, just sort of flattened out way too soon.
Okay, so that's greediness. What about the second issue, frequency bias? What's going on there?
Frequency bias is, it's almost like the LLM gets hypnotized by repetition. If an action appears many times in the input history it's given, the model tends to pick that action more often.
Even if it's a bad action?
Even if it's not rewarding. It's just swayed by how often it sees something mentioned. Almost like assuming popular means good, but in a very literal, input-driven way.
Okay, that sounds like a weird quirk. How did they test for that?
They cleverly set up input histories for the MAB task. They'd repeat the last action in the history a varying number of times, say 0 times, 10 times, up to 100 times.
To see if repeating it made the model more likely to pick it next.
Exactly. They measured something called action entropy, basically, how predictable the model's next choice was. Low entropy means predictable, likely sticking to that repeated action.
Did the models fall for it?
The smaller Gemma IIB model, definitely. Figure 4 shows a really strong link. The more repetitions, the lower the entropy, the more it picked the frequent action. They calculated its frequent fraction at like 96%.
96%. So it was almost always copying the frequent action.
Pretty much. Interestingly, the larger 27B model was much better at resisting this. Its frequent fraction was only 14%.
Oh, that's good news for scaling then.
It seems so for this specific bias. But the paper notes the 27B model leaned more towards the greediness we just talked about. So maybe it's a trade-off sometimes.
Right. Fix one problem, maybe another pops up. They linked this frequency thing to behavior cloning.
Yeah, they suggested it might be similar to copycat bias, seen when you train models just by imitating expert actions. Maybe it's something left over from the initial pre-training on vast amounts of text.
Makes sense. Okay, on to the third one, which sounds really intriguing. The knowing-doing gap.
Yes, this one is crucial, I think, for building trustworthy agents. It's the idea that the LLM can correctly reason about what it should do, but then it does something else, usually something more greedy.
It knows the plan, but ignores it. How did they measure that?
This is a clever setup. They gave the Gemma II 27B model the rules for the UCB Exploration algorithm, the one that performs well on bandits. They prompted to first think step by step, calculate the UCB scores for each arm based on the history, identify the best arm according to UCB, and then choose an action.
So they made it explicitly reason using the optimal strategy first.
Exactly, like
Right.
forcing it to show its work. And the surprising thing,
What?
it was actually pretty good at the reasoning part. It generated correct UCB calculations and identified the right action about 87% of the time. So it knew what to do.
87% is high, so it understood the task.
It understood the task. But, and this is the gap, when it came time to actually output the chosen action, Figure 5 shows this confusion matrix. It chose the simple greedy action 58% of the time, even when its own reasoning pointed to the optimal UCB action.
Wait, so over half the time it calculated the right answer, then just ignored it for the immediately tempting one?
That's the gist of it. It only followed its own correct UCB logic about 21% of the time. There's this huge disconnect between its reasoning capability and its final action selection.
That's kind of worrying for complex agent tasks.
It really highlights a core challenge. You can have a model that seems smart, that can reason, but if it doesn't act on that reasoning reliably, its usefulness as an agent is limited.
Okay, so we have these three big problems: greediness, frequency bias, and this knowing-doing gap. The paper proposes reinforcement learning fine-tuning, RLFT, as a solution. How does that work here?
So RLFT is about improving the model through trial and error, basically. The model interacts with the environment like the MAB, takes actions, gets rewards.
Right, standard RL.
Standard RL. But the key twist here is that they apply the fine-tuning based on the rewards received after the model generates its chain of thought reasoning.
Ah, so the reward signal reinforces not just the action, but the whole thought process leading up to it.
Precisely. It's learning to reason in a way that leads to better outcomes. Figure 1 in the paper shows a nice diagram of this pipeline. You generate the gate, take the action, get a reward, and then use that reward to update the model via RL.
And did it work? Did RLFT actually help with these issues?
The results look quite promising. Looking at Figure 6, for instance, which shows cumulative regret on the MAB tasks, RLFT significantly reduced the regret for both the 2B and 9B Gemma models.
So they made better decisions over time.
Yes, much better. Especially for the smaller 2B model.
Yeah.
RLFT really closed the gap between it and the larger models and got much closer to the performance of the explicit UCB algorithm. It seemed to learn a better exploration-exploitation balance.
That's great. Did it specifically tackle the greediness? Did the models explore more after RLFT?
It did seem to help. Figure 7 shows the action coverage for the 2B model. After about 30,000 RLFT steps, the coverage increased by around 12%, meaning it's trying more unique actions.
Okay, 12% is a decent improvement.
It is, though, interestingly, they saw exploration dip slightly at first before increasing, which might suggest the model initially focuses rewards on exploiting known good actions before it feels safe enough to explore more again.
Huh, interesting dynamic. And frequency bias. Did RLFT help there?
Yes, Figure 18 suggests it did. RLFT seemed to counteract the tendency to just copy frequent actions, especially when the repetition count wasn't overwhelming. The model started choosing other non-frequent actions more often.
So RLFT is pushing the model towards more reward-driven, less biased behavior. But I think you mentioned it wasn't a perfect fix. They still explored other ways to boost exploration.
Right. While RLFT helped a lot, the models still weren't always exploring as effectively as, say, UCB. So the researchers tested combining RLFT with other explicit exploration strategies.
What kind of strategies?
A whole bunch, actually. Some classic RL ones like epsilon greedy, occasionally taking a random action. Some element-specific ones like self-consistency, generating multiple reasoning paths and picking the most common action. And others like trying all actions once up front, randomizing context, summarizing context, self-correction, even adding a simple exploration bonus.
Wow, they really threw the kitchen sink at it. What worked best?
Figure 8 summarizes this. The strategy called trial, basically forcing the agent to try every single arm at least once early on, gave the biggest boost. especially for the larger model. It got the 27B model very close to optimal UCB performance.
So just forcing that initial exploration phase was really powerful.
It really underscores that the innate exploration drive of these base LLMs is often insufficient. But another really interesting finding was the exploration bonus.
What was that?
Just adding a small, simple reward, like +1, specifically for trying an action that hadn't been tried before during the RLFT process.
Ah, like explicitly rewarding curiosity during training.
Exactly. And this simple reward shaping significantly increased exploration-pushing action coverage from around 50% to 70% in one case, and noticeably reduced the overall regret. Sometimes simple nudges work really well.
That's a great practical insight. Okay, so this mostly focused on bandits, which are stateless. Did they try RLFT in a more complex setting? You mentioned Tic-Tac-Toe.
Yes, they wanted to show this wasn't just a fix for simple bandit problems. So they applied RLFT to a text-based Tic-Tac-Toe game.
How did the LLM do there after RLFT?
Pretty impressively, actually. Figure 9a shows the Gemma II Model's win rate after RLFT against different opponents. It crushed a random opponent, of course, but it also significantly improved against a decent MCTS Monte Carlo tree search player.
Did it beat MCTS?
It didn't consistently beat the optimal MCTS, but it achieved a high rate of draws, which is quite good. It learned competent play. One key detail, though. They found it was important to provide the list of legal moves in the prompt.
Ah, so giving it the valid options helped focus its learning. Makes sense.
Definitely. Without that, performance suffered.
So the paper also did some Oblation Studies, right? Trying to figure out which parts of their RLFT approach were most important.
Exactly. They wanted to isolate the key ingredients. One major finding was the importance of chain of thought.
We keep coming back to that.
Yeah, Figure 9b shows that doing RLFT without Kobe barely did better than just using standard few shot prompting with Cody. The reasoning step seems really critical for the RL process to latch onto something meaningful for exploration and credit assignment.
So the thinking part is essential for the learning part to work well. What else?
They also looked at supervised fine-tuning, SFT. Using expert data, they generated data using the UCB algorithm and trained the model either just on the actions, behavior cloning, or on the thoughts and actions, thought cloning.
How did that compare to RLFT?
Both SFT methods worked very well, essentially learning to mimic the UCB expert's low regret. This shows that if you have good expert data, SFT is a very effective approach. RLFT is more useful when you don't have an expert or want the agent to potentially discover better strategies.
Right, RL allows for discovery beyond imitation. Any other key factors?
One more interesting one. The thinking time, or token budget. They varied how many tokens the model could generate for its QOT rationale during RLFT.
Did giving it more time to think help?
It did, up to a point. Figure 9c shows that a very small budget hurt performance, but increasing it, say up to 512 tokens, led to better results. It aligns with findings in other areas. Like math problems, more reasoning steps can lead to better answers.
But presumably costs more compute.
Absolutely. There's a trade-off between performance and computational cost there.
Okay, this has been super insightful. Let's try to wrap up the main takeaways. It seems pretty clear that standard LLMs, even big ones, have these inherent weaknesses as decision-making agents. They're prone to greediness, frequency bias, and that frustrating knowing-doing gap.
Definitely. Those seem like core hurdles. But the good news is that reinforcement learning fine-tuning, especially when applied to the model's own chain of thought reasoning, offers a really promising way to overcome these issues.
Yeah, it helps them explore more effectively, rely less on superficial input patterns, and actually act more consistently with reasoned strategies. We saw improvements in both bandits and Tic-Tac-Toe.
And the work also highlights that we can push performance even further by combining RLFT with smart, targeted exploration mechanisms, whether it's forcing initial exploration or using simple reward bonuses. Guided exploration is key.
Absolutely. This feels really significant for anyone building LLM-based agents. It's not just about scale, it's about the right kind of fine-tuning to instill better decision-making habits.
Couldn't agree more. It really makes you think, doesn't it? How might these same challenges, greediness, knowing-doing gaps, play out in much more complex, maybe safety-critical, real-world applications? What kind of advanced RL or architectural changes might we need down the line?
That's the perfect food for thought. How do we build agents that not only know the right thing, but consistently do the right thing, especially when the stakes are high? A lot to mull over.
Indeed. And if you want to get into all the nitty-gritty details, the charts, the specific setups, definitely check out the original paper linked in the description. It's packed with information.
For sure. Well, thanks for tuning in to this deep dive on the AI Paper Podcast. We hope this breakdown was useful. Explore the paper, share your thoughts, and we'll catch you on the next one.